I will do that now. What do we have to prove? We are given two simplicial maps. We use simplicial maps. Which are homotopic. And we want to prove that the induced homomorphisms are the same. So F star is the same as G star. I'll rewrite this in the upper corner in the following way. F homotopic to G implies that F star coincides with G star. So F star and G star being the induced homomorphisms in homology. Now, homotopy invariance of a functor involves two statements. One statement concerns the morphisms, in this case, the simplicial maps, and here it is. But there is another statement which concerns the objects, namely the simplicial spaces, and it says the following, that if two simplicial spaces are homotopic, or homotopy equivalent, then H n of x, the homology group, is isomorphic to the other homology group, the homology group in Y, and this is true for ON. So the next step of our proof is to show that this theorem has the following corollary. So this is a theorem which we have not proved. We are now assuming that it has been proved, and I want to show that in this case, we have the following corollary, which says that two homotopy equivalent simplicial spaces have isomorphic homology groups in all dimensions. So let us assume that X and Y are homotopy equivalent. This means, by definition, that there exists a map of X to Y called F, and a map G from Y to X such that if we do the if we take the composition of F and G, then what we get is something which is homotopic to something which is homotopic to the identity of X. And similarly, if we do it the other way, we get something which is homotopic to the identity of Y. Okay, now we use functoriality to pass from these simplicial maps to the corresponding homomorphisms in homology, which look like this. So here we have F star. You have Z star. Oh, please don't confuse these F star and G stars from those up here. These are completely different homomorphisms. We have Hn of X. And by functoriality, because of this composition is the identity of the group Hn of X. Now this clearly implies that F star is an isomorphism. Well, indeed. Why is it injective? If two different points, or two different elements of this group are mapped into one element of the group HNY, then after this homomorphisms, they will be mapped, this point will be mapped to one, and so these two points, elements, are mapped to one point by the identity, which is impossible. The identity, of course, is injective. Why is F star surjective? Well, suppose that there is an element in Hn of Y where no element is mapped from Hn of X. This is the element here, it's empty, sort of, so to speak. Then, when we do G star, this element is taken someplace in Hn of X, but all the points of Hn of X are already covered. So it will be a second point mapped to one and the same point. And this again is not possible when we have an identity. So we have proved this. And this terminates the first step of our proof.
Oh, I'm sorry. There is a when you put Y composed with F, homotopic to
Oh.
identity next, then it's F composed with G. You put F, O, F.
This is correct.
Yeah, but you composed F with F.
Hmm?
The compositions, it's just a typo, let's say. To the right, to your right, right. There, right there.
We
No,
do
no, no.
F.
No,
And
no,
then
no. To the right. Where you put U composed with F, it's identity. No, 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 no. In the second line,
carefully.
there is F composed with F.
So first
And
we
it
do
should be F composed with
F
G.
to comply, then we do G, and we'll get, no.
Yeah, it was
First we
correct.
do
It's
F,
just in the second
do
line, you
I.
put F composed with F, and it should be F composed with G. Yeah, just that. But it was just a typo. I mean, the idea was clear.
So these were correct.
Yeah, those were correct. Yeah, sorry.
Let's see, I seem to have mislaid my eraser. I'll take something else for that. Okay, so I have proved this, and I can erase it and forget about it. And now I must prove this. Well, here, let me write what we are. No, I'll leave it like that. Okay. So I can erase all this. And now I am going to prove the implication there on the left. To do that, I need two definitions and a lemma, which in fact were explained last time. The definition is this. Supposing we have a morphism of chain complexes. So I'll write this like that. C prime. I'm writing this in detail. Plus one. C prime K. So this is the boundary operator. Here, we have the boundary operator going further, the K, and this is C prime K minus one, and this continues in both directions. Now, suppose that we have two chain morphisms. Well, I'll draw one and then the other. Suppose we have two chain morphisms to another chain complex. So let's call this D prime. Here we have D double prime K plus one, which takes those groups to C double prime K, and then this continues with D double prime K to C K minus one double prime, and so on on the other side. So in this situation, suppose we have a morphism F. So this is F K plus one. this will be Fk, and this will be Fk minus 1. Now suppose we have another morphism. G k plus 1 G k minus 1. So in this situation, we say that this family of morphisms, Fk and Gk, are chain homotopic if there exists homomorphisms dk minus 1 and so on, such that the following equality holds. So, okay, on the topic. If there exists a family of homomorphisms dk which are homomorphisms of C k prime to C k plus 1 double prime, and satisfy the following equality. I'll write it out and explain it on the picture in a moment. D prime k plus 1 dk plus d k minus 1 v prime k is equal to the difference between gk and fk. So let's look at the picture. What does it say? It says, what does this equality here say? It says that if first you do dk, then you do d double prime here, do d double prime here. We get something here, a chain here, and to that chain we add the following chain. Starting from here, we do dk prime, then do dk minus 1, and we get a chain here, and we take the sum of these two chains. Take the sum of these two chains. Then it turns out we require that the obtained chain is the same chain that would be obtained by applying to the given chain here gk and applying fk and taking the difference. So this is the definition of chain homotopy. And in the previous lecture, we proved the chain homotopy lemma, which says So this is a chain homotopy lemma. And it says that if Fk, Gk are chain homotopic, then F star coincides. Well, I'll write it this way: Fn star coincides with Gn star. So the proof of the chain homotopy 11 was given in detail last time. And so we conclude that we have now proved this statement. We can erase this. The proof has been obtained. Now, moreover, we can erase the statement because we need not come back to it. What it remains for us to do is to prove that there does exist such a decay, such a family of decays, which satisfy this equation. Okay, so I can now erase everything here and get to work on the next step of the proof, which is to show that under these conditions, there exists such a family of decays. However, I'm going to modify a little bit what is written here, because I'm going to apply this statement, which is purely algebraic, in a concrete situation. I will here consider Ck of x and I here Ck plus 1 of y and the differentials here will be the one for y and the one for x. No, this is also for y. No, the one for x here. Okay. So this is what I have to prove. To do that, I will need another new notion. In fact, a couple of new notions and another lemma. So this, according to the booklet, is section 6, and it's called a cyclic support. So we begin with a definition on a simplicial space. X is a cyclic if its homology is trivial, which means that h n of x is 0 if n is greater than or equal to 1, and if the integers for n equals 0. Speaking more intuitively, a simplicial space is acyclic if it doesn't have any homology. The next definition is this. The support of a chain is the space or the subset of all its simplices with non-zero coefficients. So if we're given a chain, what is a chain? It's a linear combination of simplices with non-zero coefficients. With certain coefficients, and we take all the simplices which have non-zero coefficients. They form a subset of X. Oh, just a moment. Пожалуйста, уходи, пожалуйста. Okay, so this is the support of a chain. And now we will need a lemma, which is called the cyclic support lemma. It says the following. In our situation, when we have these chain homomorphisms,
sorry, Professor, we cannot see that board.
pardon me? So supposing we're given these two maps and assume that they are augmentation preserving.
Professor?
So assume that these maps are augmentation preserving. Augmentation preserving maps were defined in the previous lecture. I will not come back to that definition.
Sorry, Professor?
Yes.
We cannot see that board.
Pardon me? What voice?
We cannot see that board. No, the camera,
Board.
yeah, the camera doesn't cover that board.
Is that better?
And it's not enough yet.
I can see it.
Oh, really?
No.
Yeah, I can see it.
But,
Maybe do you,
No. Do you see the? Do you still see the bigger board?
yeah, I can see everything. Maybe do you have it in your phone or like laptop? Maybe if you put it horizontally, because I can see everything.
uh, uh, okay, so can you see everything
You
still
okay
now?
now? Okay. So, supposing we have these segmentation preserving homomorphisms, and to any simplex dk, I will omit the superscript k. I assign a certain subcomplex denoted AK. Well, I'll write K not small. I'll omit it from now on. This is a subcomplex of Y. And I'm going to assume three things about it, about this assignment. Before writing out here, I'll draw a picture to show you what's going on. We have this space Y here. We have a space X. We have a map, a simplicial map. Um, oh, no, no, we just have these spaces. Now, if we take a simplex here, so this is a simplex here, and then the assignment A takes it to, so this is A, or certain subcomplex of Y. Now, this assignment must satisfy three conditions. First of all, any simplex delta K, A of delta is acyclic. The second condition, if delta K contains a face, a subsimplex delta K minus 1, then we require that A of delta K contain A of delta K minus 1. And finally, we require that A of delta K supports F of K supports the chain F K of, so I'll write it this way. The chain F K of delta K. Now, here, delta K stands not for the simplex, but for the chain consisting of the simplex multiplied by +1. I will not write this +1 here. So this chain must support this and also must support GK of the same chain. So let's look at what happens here. Here, we require that the image, that if we take Fk of this chain, it will be some chain here. So to this chain corresponds a chain here, which is supported by A of K. So this green thing is inside the red thing. And this was here Fk. Now, also, GK to this chain assigns a chain here, which may intersect or may not intersect the other chain, doesn't make any difference. And it is also contained in the red simplicial subcomplex. So under these conditions, the cyclic support lemma asserts that in this case, we have this statement, which I'll denote by a red star. So let me repeat the statement. The cyclic support lemma says that if you have two augmentation preserving homomorphisms of a chain group CK of X, CK of Y, and if there exists an assignment that to each simplex of X assigns a subcomplex of Y, which is first of all a cyclic, which has the property that if we take a face or subsimplex of a simplex delta K, then the assignment gives us something which contains the simplex. Finally, it has the property that A of the simplex will support both the chain fk of the delta k and the chain gk of delta k. So this is the statically support lemma, and we will now proceed to proving it. So this is the next step of our proof, which will be, in fact, the final step. So what must we prove? We must prove that there exists a sequence of homomorphism dk of ckx to ck, which satisfy this equality. So prove this by induction. Proof by induction. So we should start with k equals 0, which will give us the base of induction. And I will not explain why the base of induction is true. This is not obvious, but it's very carefully written in the booklet. So just read the booklet. It's maybe 10 lines in the booklet, which explains why you have the base of inductions. And what we're going to do is the induction step. Supposing we have already constructed D0, D1, and so on, Dn minus 1, satisfying this condition, are constructed. We must construct Dn that also satisfies this condition, which means precisely this. I want to write out this condition in a slightly different way. I will write it as dy n plus 1 dn. Now I'll write dn in red because I don't know dn. I know everything else in this equation, but I don't know dn. And I will send all the rest of the stuff to the right-hand side. Is equal to gk minus fk minus d0 d k minus 1 dxk so I have to construct the dn which satisfies this condition. To do that, I'm going to denote the right-hand side of this equation by Cn. And I will compute dy n of Cn. Going a little bit ahead, I will show that this expression is really equal to 0. Computation will show that this is equal to 0. This means that this concrete cycle chain is a cycle for any fixed simplex. Now, since it is a cycle, we will show that it follows from the conditions of the acyclic support lemma that this cycle is really a boundary. This is because there is no homology in A of k. And so we'll simply define dk dn as the co-boundary of that cycle. So you can forget all this. Let's start over again. I have to construct a dn such that satisfies this relation. I am computing the boundary of Cn. And so it is equal to the boundary dny gk minus the boundary of gn. Sorry, these have been n all the time. N minus 1 dn. Sorry about that. dn dnk fn, and then minus d y n of d n minus 1 to d x n. Okay, so we'll continue calculating this. Now let us for a moment look at this expression here. What is this expression here? by the induction hypothesis, we can rewrite this as follows: minus f n minus 1 minus minus g n minus 1 g n minus 1 minus f n minus 1, and then minus d n minus 2 d x n minus 1. And this here we have dk dn x. So I will simply recopy. N minus so I have the following expression. And now let us look at what's happening here. Well, first of all, we have the composition of successive boundary operators. And so this is 0. And now here we have g n minus 1 d x n and let's compare these two things, this and this. Well, I claim that they're equal because if you look at the diagram, which unfortunately I was not able to leave on the board, of the chain morphisms, we have a commutative square. And so dny of, when we first do gn, we go down, and then we do dny. And here we first do dxn, and then we go down. And since these squares all commute, we have the equality of these. And they have opposite signs, so they cancel out. Similarly, this expression minus f n minus 1 by d xn will cancel out with this expression, because the other commutative, the other square is commutative. So we have finally obtained that this is 0. So, okay. So we have shown that this is a cycle. Now, let us look at the n of some chain consisting of one simplex, dn. Now we have shown that the boundary operator of this chain is 0 which means that this chain is a cycle. Now it follows from the conditions of the lemma about acyclic supports that there is no homology in A of delta K. And this lives in A of delta K. Therefore, there must exist some cycle, some chain. So there exists a chain in Cn plus 1 of y, whose boundary is the whose boundary is the chain Cn, the cycle Cn, and which denote this chain by dn of delta n. So we have defined dn of delta n for a chain consisting of one simplex. We generalize that to any chain by linearity. And so we are done. So we have proved the fact that such a sequence of homomorphisms exists, and this concludes the proof of the homology invariance of simplicial homology. Okay, the last remaining thing that I will tell you today is something which is called the Hurewicz homomorphism. And I will state and explain two theorems that are related to the Hurewicz homomorphism. And this homomorphism is a sort of a link between homotopy and homology. And the theorems, especially the Hurewicz theorems, gives conditions under which homotopy and homology are the same. Okay. So we have the following. Uh, so what is the range homomorphism? It's a homomorphism from P n of x to P to H n of x, where x is simplicial. It's a simplicial space. And it is defined in the following way. Let's take an element of here. It is a spheroid, or rather, a homotopy class of spheroids. So let us take some concrete spheroid in that homotopy class and replace it by another spheroid by using the simplicial approximation theorem. So this is simplicial. So we had any spheroid, and now we have a simplicial spheroid. Now, this simplicial spheroid consists of n-dimensional simplices. So write +1 on each simplex of sigma hat of S1 Sn. Sn is the sphere that we map to obtain a spheroid. So this will be a chain. And this chain, by definition, is by definition H of sigma. Of course, we have to prove that this is well defined. This is indeed the case, but it's not simple to prove that. The proof, unfortunately, will be omitted. So we have defined the Hurewicz homomorphism. Now, I will state the Hurewicz theorem. If X is a simplicial space, such that I1 of X is equal to pi 2 of x is equal to pi n minus 1 of x, and is equal to 0, then h n of x is isomorphic to pi 1 of x. And this isomorphism is given by h. By h star. So I will not prove this theorem. The proof is rather complicated. There is a sketch of the proof in the booklet, which is not at all convincing. I will do some hand waving, which hopefully will help you understand why the theorem is correct. Now, what is the difference between homology and homotopy? Well, there are two differences. In a homotopy, the elements of the homotopy group are spheroids, so they're kind of like circles or spheres. The elements of a homology group are cycles, and cycles can be more complicated than spheres. They can have, for example, they can have handles. Now, this condition here. Now, a cycle can have a handle which contributes an element of the homology group of lower dimension, say n-1 here. Now, this condition does not allow us to have cycles with handles. So the cycles are like spheres. So the cycles are like spheres. And now, what about the triviality of a cycle in homotopy and homology? In homotopy, it means that we can contract the spheroid to a point. In homology, it means that the cycle bounds something. Now, a sphere will bound a disk of the next dimension, whereas here, our cycle can be bounded by something more complicated than a disk. It can have handles. But no, in this situation, it cannot have any handles because we have this condition. Okay, this is not a very convincing argument, but maybe some of you did understand that it is reasonable to expect this result. For the proof, well, there's a book by Prasilov called Elements of of homology theory. Where this theorem is proved in detail. And one last theorem before I conclude. This is the Poincaré Abelianization theorem. And it says the following. The one-dimensional homology group of a simplicial space is isomorphic to the following Gaussian group. Where pi1 x comma pi1 x denotes the commutator is the commutator subgroup of pi1 of x, which means that this by definition this equals by definition the set of all expressions of the form a1 b minus 1 ab or a and b are elements pi1 of x. Now, if a and b commute, then this expression is equal to 0. Or another way of putting it, this expression is equal to 0 if and only if a is equal, a and b commute. So we are canceling out, so to speak, those elements that do not commute. So we're Abelianizing the group pi1 of x. The proof of this theorem is not too difficult. Let me sketch the proof in the case when pi1 of x is finitely presented. So it's given as a1 and so forth, a n with relations r1 equals to r s. I think we use this notation for group presentations. Okay. So supposing pi 1 of x is a finitely presented group, then what this theorem says is that if we add to these relations all possible relations of the form a, b, a negative 1, b negative 1, if we add all these relations to that, then what we obtain will be the homology group. If we look at what the Hurewicz homomorphism does, well, it does just that. An element of Pn of x can be regarded as a closed curve, possibly with self-intersections of one-dimensional simplices. And the corresponding chain corresponding chain will be would be a cycle provided that elements of this cycle commute. So I will not explain this further, and let me stop at this point. And just say a few words to conclude today's lecture. So we proved with a lot of effort the fact that simplicial homology is homotopy invariant. Why was this proof so difficult? Well, because from the point of view of category theory, this is a wrong theorem, because simplicial homology has to do with simplicial spaces, and its definition involves of topological spaces. So this homotopy ignores the simplicial structure of the space. For this reason, this is a sort of a badly stated theorem, because we are talking about homology groups in one language, and in the homotopy of spaces in a completely different language. This is the reason why these things are so difficult. What one can do, of course, is to define something which would be natural to call simplicial homology. This can be done and has been done, but and then the proof that simplicial homology theory is an invariant of simplicial homotopy becomes much simpler, but traditionally it's not. It doesn't really interest anyone, and the theorem that we prove is the one that is really used in practice. And so that's all for today's lecture. I hope to see you next week.
See you. Bye.